very resilient, very durable, non-combustible material. Basalt rock makes up the primary ingredient within our materials. So just kind of leave you that lasting impression. You can go ahead. And so, some of the benefits here, clearly non-combustibility. I think people are very familiar with the use of mineral wool to meet fire code requirements in various applications. When we talk about passive house, or we talk about high performance facades and adding insulation to the exterior of buildings, that becomes much more paramount. When we talk about long-term performance of our facades and our buildings in terms of trying to reduce carbon emissions, but have buildings that last a long time, thermal stability is really key. So these products will last a lifetime in terms of providing that R value that you need. Water repellency, I'm not going to talk about that right now because we'll talk about it for the next 45, 50 minutes. And as we're building more high performance facades, adding air tightness to our enclosures and lots of thermal insulation, we're reducing the heat flow across our walls, which again, we're going to talk about today. And in doing so, our walls don't dry out as quickly. So thinking about vapor permeable materials is really critical in that design side. And so stone wool and rock wool insulation really can provide that diffusion and that drying capacity that buildings need. And then lastly, acoustics, which is ever driving a lot of project needs, particularly for hospitals, residential buildings, schools, et cetera. And we can really provide a high OITC, high STC rated assemblies, or contribute to them. So we can always talk about that. And we're not just a bad insulation. I won't get into all these things, but I think many of you are familiar with our exterior grade rigid products for walls, as well as roofs, as well as below grade. That's, I just want to imprint that we do offer a lot of applications. And we are the leading supplier of stone wool insulation in the world. We have currently 4 facilities in North America. We're coming on board with our 5th facility next year in Ranson, West Virginia, to really service the demand of the Northeast. So we're excited about that. And so today's presenters, just to again imprint, these are the technical people from our team. Antoine Havillon serves as our building science manager. We offer really great support in that realm, and you'll get a sense of that today. But he has master's in engineering and master's of architectural science, and has a tremendous amount of experience dealing with things from BIM to WUFI assessments, hydrothermal analysis. I'm excited to have him here to kind of speak to that degree. And Alejandra Nieto also has a very high science background. She serves as our R&D program manager, or project manager, I should say. So a lot of the initiatives that we get involved with in kind of exploring different products, different applications, addressing specific needs in the market, that's where she drives the operation. So yes, very excited to have them here. And so this is an AIA CEU, so you will get a credit for this. I think Andreas is handling that. So I think everyone's already registered for that. But without further ado, I'm going to hand it over now to Alejandra and to Antoine to move forward with today's presentation. So hopefully you enjoy it.
Thank you, Todd. Good afternoon, everyone. So today's program will be covering some building science fundamentals as it relates to moisture control. Then we'll be talking about how stone wool can be used in some exterior wall application. And we will also discuss appropriate rain control and vapor control strategies for wall assemblies. And finally, we will review some in-situ examples, some actual case studies. So first of all, why moisture control? So moisture control is really important because it is actually involved in most building enclosure issues. And moisture issues can be small things such as discoloration, staining, some odors, but can also become much more problematic as it can create corrosion, rot in case of wood framing, for instance, freeze-thaw deterioration in the case of masonry buildings, for instance, especially like buildings like in New York City, like retrofit of masonry buildings. And it can also cause problems, obviously, to occupants, maintenance personnel, building owners, and so on. And so moisture control basically consists of making sure there is no water penetrating or condensing in areas of a building that must remain dry. So obviously the enclosure, for instance, but also consists of limiting the number of areas of a building that can, get wet. such as bathroom, kitchen, and so on. And so what's important is to design a building with moisture control in mind, and therefore to design, construct, and operate the building, trying to avoid as much as possible to use vulnerable materials in areas that get wet, but also to make sure that when we have to use materials that are vulnerable to moisture, to make sure that they don't get wet, and that if they get wet, that they can dry out quickly. So this this idea can basically be summarized with what we call the moisture balance. So the moisture balance is basically the idea that there must be some balance between the amount of wetting and drying that you have with your building enclosure. And so if you have a balance, you will be sure that moisture does not accumulate over time. Realistically, what you want is to make sure there is more drying than wetting, and that if there is wetting, the wetting will not be lasting for a long time. So if your enclosure in one area gets wet, you want to make sure it's going to dry quickly. So the moisture that is there for sometimes will not create any damage. And realistically, buildings will do leak or will leak, even if we build them really well. Eventually, sinks might fail here and there, some joints, and you may end up with a little bit of leakage around like fasteners, penetration, window frames, and so on. So it's absolutely key to design with this moisture balance in mind. So now we didn't, if we look back, and we never really used to care so much about moisture control, or at least not in the same way that we do today. And this is because our buildings have changed a lot. The way we built and design our building has changed a lot. So the number one thing that comes to mind is the increase of thermal performance. So obviously buildings used to not be very well insulated, if insulated at all. And therefore there will be enough heat loss and air leakage to drive the enclosure at all time. We have also increased the air tightness, especially with passivas, as you know, and there is a lot less air leakage and heat moving through our assembly to dry it. We're also using more and more materials with lower vapor permeance. And so, we're using with OSB, precast concrete, many types of cladding that are like, metal panels, things like this. We use vinyl, polyethylene sheet as like 6 mil poly on the inside of our walls, and so on. So all these materials have a very low vapor permeance, which means that if moisture penetrates our assembly, it's going to have a very hard time drying. We also use materials that have an increased water sensitivity. So when we use to, build out of solid masonry or, solid wood timbers and so on, we now use OSB, plywood, gypsum sheathing, materials that are really sensitive to moisture and which can really degrade quickly when they are exposed to moisture. A lot of these materials also have a very low moisture storage capacity. Like a gypsum board can really not hold any moisture. But also we're building a lot of buildings with stick frames, meaning, we put materials with low storage capacity in the middle of metal studs, wood studs, and this can really not store any moisture. When back in the day, we will use masonry, for instance, like solid masonry, which really could, hold moisture during a big rain event, for instance, and then it will dry out when it gets sunny again. But the moisture will be stored by the masonry and will not penetrate further into our buildings, whereas the materials we use today cannot do this. And finally, and probably a very important one, is the fact that while the stick frame buildings, they are basically hollow enclosures with a lot of connected voids. So, you will have your wall, your stud cavity that connects maybe with your ceiling plenum because, the interior finish is not going all the way to the ceiling and so on. And so this big connected void can really increase the risk for like convection within these voids, and therefore air leaking, like interior moist air leaking into this void, bringing moisture and moving throughout our assembly and potentially creating condensation in places. So if we look at our assembly, and here we'll focus mainly on walls, there are many different wetting sources and mechanisms. So there's a lot of different sources for water to penetrate our walls. So the first one, the most obvious one I would think is the rain. So obviously we can have rain absorption, like a brick veneer, a brick wall, a CMU wall absorbing water. We'll have penetration. So it could be penetration in cracks, for instance, like in the mortar crack in our masonry wall, for instance, but it could also be penetration behind the joints of an open joint cladding. And then we will have like splashes and drips. A second type of movement will be the water vapor movement. So it could either be vapor diffusion, so diffusion of water vapor through the layers, through the material of an assembly, but it could also be movement from convection, so air leakage, basically, air leaking through our assembly. Then there is the built-in moisture. So the built-in moisture will be the moisture which is in our assembly from day one. So, you know, it could be a concrete wall which has been poured and we waited for it to dry to some extent before continuing building the enclosure. But, you know, this concrete will continue drying for several years and it will be holding some moisture, but it could also be like a wood sheathing that remain exposed for sometimes before the membrane and the insulation and cladding were installed. Or it could be like insulation that was not properly stored on site and maybe got, you know, go wet or something. And finally, we have as a source of moisture, the moisture coming from the ground, which could be also diffusions from the ground to our through our foundation to our basement, gravity from the rain, capillary, which is really important, which will be the moisture leaking to our from the ground to our foundation and so on, which we will take care with like capillary breaks and things like this. So a good and well-known way, I would say, to deal with moisture is to design according to the principle of the perfect wall, which you know, Joseph Seabrick from Building Science Corporation and John Straub have you know, made popular. And so the idea of the perfect wall will be to have basically all your control layers, the control layers that relates to moisture on the exterior side of our structure. So we will have, you know, our concrete or CMU or wood studs or steel frame and so on. And then we will have external to this all our control layers, which will be in order of importance, the water control layer. So the water control layer will make sure liquid water doesn't penetrate. So this control layer could be perfect. For instance, it could be like a window. Obviously, the glazing is a perfect barrier to rain. Or it could be like a drain system in you know, a rain screen type of assembly, or in a you know, stucco or IFS assembly, for instance. Or it could be a water resistive barrier. We will then have the air barrier. So the air barrier could be done also in many different ways. It could be a membrane, it could be air impermeable insulation that is taped. A window obviously would be an air barrier and so on. Then we will have our insulation on the exterior of this, possibly on, if possible, exterior to our membranes. So basically the insulation will protect these membranes, the water and air barriers. And so this insulation also could be, the thermal layer, sorry, could also be like a radiant barrier, like a foil in a roof system, for instance. And finally, and again, as I said earlier, in order of importance, the vapor control layer. And the vapor control layer could be simply the materials that we already have, like, you know, a plywood or like an OSB sheathing, but it could also be like a vapor barrier, obviously, like a 6mm poly, a foil, a craft paper on a bat, and so on. It could be a vapor retarder, so actually a craft paper, a craft face bat. The craft paper itself will have a bit of a higher permeance, so that would be a vapor retarder, a permeance of about 1 perm. Or it could be like a smart membrane, or it could be also paint, like a latex paint, which would be more like a class 3 vapor retarder, so something around 7 to 10 perms. So still doing some vapor control, but a lot more open. Latex paint on an interior finish, for instance. And finally, we will have the interior and exterior. Obviously, here we're focusing on moisture. So in reality, we will also have to consider fire and sound control. So when I say the layers here are in order of importance, when it comes to moisture control. So if we focus more on the rain screen system, which is really popular nowadays, basically the rain screen system kind of followed this idea. So we will have the rain screen cladding, which will basically deflect most of the rain. And then we will have potentially open joints. Therefore, we will have a drainage space behind, which could be either just a drain space, it could be ventilated. And so this drainage space would be used as a space to basically drain the remaining of water, also ventilate to provide drying to the cladding, to the backside of the cladding. And it could also help provide convection for the insulation to dry faster. And it will also provide like a capillary break between the cladding and the insulation or the backup wall. And then we will have our flashing, drain opening, and so on. Obviously, this definitely follows the perfect walls concept, even though obviously nowadays because we built with stick frame, we usually put bad insulation in our cavity. So we'll talk about this in a little bit. So I think for the rain aspect, it's quite well understood how we deflect rain. It doesn't mean it's always well done, but I think for the most part, we well understand it. So now let's focus on vapor diffusion for a bit. So there is a major difference between water vapor and liquid water. And the reason is that basically liquid water is a cluster, a group of water molecules all together. And therefore liquid water is large. You will have liquid water will be a big cluster, a large cluster of water molecule, whereas water vapor is basically made of water molecules that are like alone. And therefore, water vapor molecules can pass through much smaller opening than liquid water. And that's why we can have, for instance, a water resistive barrier, which will stop liquid water because the cluster of molecule cannot pass through the grid made by the membrane material, but a single water molecule can pass through. And so the water vapor will occur through porous materials. And so, for instance, it could occur through mineral wool, which is highly vapor permeable, but it could also diffuse through drywalls, through plywood, and so on. So lots of material will be, porous, and therefore water can diffuse through them. And it's driven by a vapor pressure difference. And so vapor will go from a high vapor pressure to a lower vapor pressure. So, for instance, if we think about the city of New York, a lot of the time, you will have a heated interior, and you will be, colder and drier outside, and therefore moisture will go from inside to outside. Vapor diffusion is important, not so much because of the amount of moisture that can come into a wall because of vapor diffusion. And this is where I think there is a bit of a misunderstanding here often. Vapor, we always think as vapor diffusion as a problem because it will allow for moisture to come inside our wall, and therefore we'll think about vapor barriers and so on. But if you remember earlier, I said in order of importance in the control layer, the air control layer was a lot more important than the actual vapor control layer. And I will try to explain a little explain this a little further. But the reason why vapor diffusion is so important, it's not because it brings moisture inside our assembly, but it's mostly because it's the main drying mechanism for most of our assemblies. It's basically with vapor diffusion that moisture inside our wall or inside our enclosure will be able to get out. So assuming water has got inside our enclosure, vapor diffusion is pretty much the only process that will allow water to get out. And obviously, if water comes in, vapor diffusion is still important because, we may have problems with this water vapor diffusing through our assembly once it's inside our wall and potentially condensing on a cold surface. So for instance, we've all heard about the dew point, and the dew point is this temperature at which basically a certain volume of air with a certain amount of water is going to condense. And so the idea is to make sure basically our dew point falls inside our assembly. So diffusion is also important from that standpoint. So for instance, I think we know that putting exterior insulation also allows us to keep our sheathing warm, which often represent the sensitive surface in an assembly, the first cold layer in an assembly. And so using exterior insulation will allow for vapor to diffuse through the assembly without condensing within the assembly. And so there are obviously different ratios of insulation when we do split insulation that we have to follow and so on. The warmer the climate is, the less at risk, you know, our sheathing will be regarding vapor diffusion. So, you know, we talked about vapor diffusion, and again, I said vapor diffusion in terms of how much moisture it brings inside the wall is not a big deal. So if we look at this example, so here we're considering a 0 degree Fahrenheit on the exterior side, a 70 F on the inside, and about 35% RH on the inside and 80% RH on the outside. So quite, you know, quite typical. Obviously, these are temperatures and conditions that can be seen in New York City. And so if we look at our first wall number 1, which is a wall with a class 2 vapor control layer. So let's imagine a batt insulation with a craft paper on our batt. The amount of moisture which will be brought inside our wall for, you know, the given size here, that all this, the walls we're going to talk at the exact same size, obviously. The amount of moisture that will be brought inside the wall because of vapor diffusion will be 48 grams per month, or 3 tablespoons, but whatever it is. Now, if we change this, the craft paper to a class 3 vapor control layer, so we use the same batt, but instead of having a craft paper, for instance, we will just have latex paint on our gypsum board. Well, this amount of moisture is going to increase by about 10 times. So a little more, but we will end up with 538 grams per month, whichever it means it's a lot or not. It doesn't really matter here. It's not much, but you know, maybe this amount don't really mean anything to you, but it's the scale between these different scenarios, which is important more than the numbers themselves. Now, if we look at a wall number 3, so same wall, but now we have a class 1 vapor control layer in this wall. So now we have a proper vapor barrier on the inside, but we allow for a 1 square inch opening. So basically we allow for some air leakage, pretty much typical air leakage. And we end up with 22,200 grams per month. So if I'm right, that's about what, 500 times more, something like this. Yeah, I think it's about 500 times more than the first scenario. So air leakage, a little bit of air leakage, it can potentially bring a lot more moisture in our assembly. So this is really what we want to focus on. So now we could talk about air barriers and you know, how to make building airtight for ours. And I think in the passive house community, that's a topic that is actually pretty well known. So for the purpose of this presentation here, we won't spend too much time on it, but just to remind everyone, even though I assume for a lot of you guys, it's probably clear already, you know, an exterior air barrier approach where we will install an air barrier on the exterior side of our sheathing is always better because it's much easier to detail and it's protected. In case we use exterior insulation, it will be protected by the exterior insulation, by the cladding and so on. So the interior air barrier approach, where we would rely on like the vapor barriers to be sealed and or maybe the interior gypsum board to be sealed and so on. It's a lot more complicated to do. It's probably riskier because that's close to where people might install cabinets and so on. So the exterior air barrier approach, always recommended. So now if we talk about the influence of moisture on stone walls. So if we look from a theory standpoint, basically, here's what we can say. So stone wool does not absorb water, and stone wool is water repellent. Why? Well, it's not because the product itself, the fibers themselves are water repellent, but they do resist water absorption because when we manufacture stone wool, when stone wool is manufactured, every single fiber gets coated with a water repellent coating. And so basically, during the manufacturing process, when we get the fibers created, at the same time we spray the binder, like the glue that basically keeps the fibers all together, we also spray a water repellent coating, which is going to cover the fibers. And that's what makes it fully water repellent, even if you cut the board and so on. So it's a non-hygroscopic material, and it does not take up and retain moisture from the air. However, stone wool is highly vapor permeable. As a matter of fact, it's about 98% porous material. Obviously, it depends on the density, but it's so, you know, the difference of density is so small compared to how porous the material is. It's still always about 98%. So it's a fully open material as opposed to other, you know, closed cell insulation foams, for instance. And so it is defined as a vapor permeable with a of about 40 perms. This permeance will vary based on the thickness of the insulation, the density of the insulation, but because it's so permeable, again, it will be always about 40 perms. So it has a high drying potential. No, can stone wool be soaked with water? Yes, obviously, if you know, it's subjected to floating, or if you know, you have a bad detail of an exterior wall, you have an open joint cladding, water penetrating behind your cladding, and let's say the insulation is sitting on the Z-girts, and the slope on the you know, horizontal Z-girt, and the slope of the Z-girts is sloping towards the sheathing as opposed to the cavity and the drain. Obviously, eventually, water could sit there, and the insulation could eventually get wet. So the insulation on its own will not get wet, but if the insulation is wet, it will. It's basically the result of you know, a poor design or improper installation or something.
Antoine?
Like this. Yeah.
Antoine, it's Todd. I don't want to interrupt too much, but there is a series of similar questions that have popped up in the chat box, and it just relates back to a couple of slides ago where you kind of explained the 3 wall types and the importance of air tightness on the interior side. And then the subsequent slide, you'd indicated that it's better to put the air barrier on the outside. And so I was just wondering if you could explain or provide some clarification there for the audience.
Yes, so in this example, we were relying on an interior air barrier. So maybe that was one of the things that was unsure. So we were relying on the class 1 vapor control. I don't know, Alejandra, if you can come back to slide 18. But basically, yeah, thank you. On the case number 3, on case 1 and 2, we assume there is no air leakage, obviously, that we are fully airtight. It's a calculation, a handmade calculation, so we can do these kind of things. Obviously, it's not super realistic. But in case 1 and 2, we're assuming 0 air leakage. In case 3, we're assuming some air leakage. Because you know, you wouldn't have the exterior air barrier, so you will have air leakage. Typically, that's why there is a little outlet box shown on the drawing. But basically, you know, you will have some air leakage around an outlet that has not been sealed, for instance. And that's why, you know, installing the air barrier on the sheathing is always recommended, because well, you don't have to, you know, obviously you have to detail things, but you will detail them one time. Whereas if you do it on the interior side of the wall, every time you move an outlet, you know, you install a frame or something, you make a hole, technically you will need to seal that hole.
Right, but wouldn't that mean that you're pretty much guaranteed to have air leakage on the inside if you're not intending to have an air barrier there? So that I'm just curious, you know, why. To
so
me,
you're saying if you have the air barrier on the outside, would you not have air leakage inside your cavity? Is that what you're saying?
Well, I'm trying to get clarity. I think that's what the audience is trying to get clarity on. Is that so? If we put an air barrier on the exterior sheathing and not on the interior, would we not still see the situation that's happening in wall number 3?
Okay, I understand. Well, it depends. If you have your air barrier on the exterior side, what could potentially cause air leakage? It will need to be, again, a pressure difference. So in order for air movement to occur, pretty much you will need to have a hole that goes from inside to outside. So if there is no hole in your air barrier on your sheathing, there is really no reason for the air to take that, from the interior air to take that direction to go inside your wall and try to go through your sheathing, because there is no pressure difference. Now, could you have air loop coming from inside, looping inside your into your stud cavity and not trying to go outside, just looping, having convection loops inside your stud cavity? Potentially, yes, it's possible. If your cavity, for instance, is filled with batt, even though batt insulation, whether it's fiberglass or, you know, stone wool, or even if you think about cellulose, this kind of product, it's not, obviously, they're not airtight product, but they are permeable to air, but they're sufficiently resistant to air that there's not going to be a significant amount of air movement through the insulation itself. Now, if your cavity is not filled with batt, and you have, for instance, you take the bat, you keep it on the inside, and you leave a big air cavity on the exterior. You know, let's say you have a 6-inch stud cavity, you have a 3.5-inch bat, and the bat is toward the interior side. So you end up with a 2.5-inch gap next to the sheathing. Potentially, yes, you could have air, even if your air barrier on the sheathing is good. For sure, you could have air moving inside this cavity and potentially interior air moving through that through the insulation to this cavity and potentially condensing on the sheathing. That's why we always recommend to push the bat against the sheathing. So yes, you may end up with some air movement, but the air movement is not going to occur through the insulation. It's going to occur through air. It's easy.
Justin Taylor also made a good point that for high performance facades, you would typically see exterior insulation on the outside as well. That's going to keep the sheathing warm, dry, and stable so that the condensate, I would assume, would not be happening there anyway for those types of assemblies.
Absolutely, but you may still have thermal bridging because of cladding attachments, you know, fasteners and so on. So in any case, whether you have exterior insulation or not, I would always recommend, if the cavity is not filled, to push the bat against the sheathing. So you don't have that air movement. So you will have air movement in the cavity, but on the interior warm side as opposed to the exterior side.
Very good. Thanks, Antoine.
Yeah, no problem. Okay, so back to slide 21, and I will leave it to you, Ali.
So just going on, continuing on with the conversation about how stone wool is essentially designed and manufactured to repel moisture and to have that capability to drain moisture. There's still misconceptions in the industry in terms of, because stone wool is a vapor permeable insulation, that when you install it on the exterior side of your assembly, where it's going to be exposed to rainwater, higher moisture potentials, that, you know, it's not going to perform adequately because it's just going to soak up all that moisture and not perform, right? Especially when we're talking about behind open joint cladding systems that definitely allow some rainwater to reach the sheathing, or if you have exterior insulation, to reach the exterior insulation. So what we did was we decided to conduct a laboratory test to kind of validate and quantify, you know, how much water is the insulation actually seeing behind an open joint cladding, and then compare it to what would be known as a common insulation type that's readily, how would you call it, readily accepted in the industry. So we decided to compare it to a foam plastic, and in this case, we looked at XPS assembly. And so we conducted this research study with Building Science Laboratories, now Building Science, RDH Building Science. And so essentially what we did was that we built 2 full-scale mock-up wall assemblies that were representative of actual rain screen or drained wall assemblies. And so they were tested to quantify the amount of water that reached the insulation behind the rain screen cladding, and then determined the drying capacity and the drying rate. So the 2 walls that we evaluated, again, we evaluated one with stone wool insulation. In this case here, we used 3 inches of the stone wool semi-rigid continuous insulation versus an XPS assembly that we used 2 inches. And so the difference in terms of the thickness of the insulation in this case here, because it's in a laboratory setting where we're not exposed to exterior conditions, different temperature fluctuations, the difference in thickness and the difference in R value didn't play a huge impact on the overall performance evaluation of this assemblies. And so essentially, if you look at the schematic here, so we had the framing, we used a gypsum sheathing, then we had the exterior insulation, a vertical Z-grit to create that the air gap, and then the open joint cladding. So in order to be able to physically see behind the cladding, we used a series of plexiglasses with 1/2-inch gaps in between them, essentially to be representative of an open joint cladding, but we wanted to be able to see them. And so these 1/2-inch openings between the cladding panels was approximately equated to about 8% of open area on this wall assembly here. And so what we did was we used the ASTM standard spray rack method to spray water onto the wall assembly. And so this test, if any of, I don't know how many of you are familiar with ASTM standard testing, but essentially we're looking at a very high amount of water that is being sprayed onto the wall. So we're looking at approximately 5 gallons per square foot per hour. And so this is a significant amount of water, in essence, to look at worst case scenario, extreme worst case scenario in this case. And so just wanted to point out that this water is essentially, you know, much higher than what a typical driving rainfall would be hitting on a regular exterior wall. So as an example, if we were in Toronto, the amount of water that was tested was approximately 70 times higher than over 95% of driving rainfalls experienced in Toronto. And so in order to quantify the performance, essentially what we did was we included a series of drainage troughs to collect water at the different drainage planes within this assembly. So we had a drainage trough collecting water on the exterior side of the cladding. We had a second one that was collecting water that was draining off the back side of the cladding. A third one to collect water that was draining on the exterior face of the insulation. And then a fourth trough to collect water that was draining in front of the sheathing. So essentially in between the sheathing and the exterior insulation to evaluate how much water is actually getting through the insulation itself. And as I mentioned, these tests were conducted in a laboratory setting, so they weren't exposed to any kind of exterior conditions, any kind of different temperatures or wind that could potentially impact the drying potential. So to assess the assemblies, we looked at 3 different things. So we looked at the measured volume of water that was collected from each of the surfaces in the drainage troughs. We then looked at the amount of water that was actually stored within the assembly following the water application. And then we also looked at the length of time required for the wall assembly to dry any of that stored water. And so off the bat, the first thing to note was that the study indicated and demonstrated that over 85% of the water that was collected from the drainage troughs were collected either on the exterior side of the cladding, the interior side of the cladding, or the face of the insulation itself. So what that means is that very little water actually is penetrating behind the insulation itself. Actually, only 0.1% of the water was actually collected in the drainage trough between the sheathing and the insulation. And the remaining water is water that we can assume was either stored within the assembly, but also a lot of that water was actually also just directly deflected off the assembly from the water being sprayed onto the cladding itself. And so what we're seeing here is the results. Multiple tests were conducted, and so this is kind of results of a few of them to kind of demonstrate consistency between the testing and consistency between the performance. And so if you look at this graph, what you'll note is the top cluster of graphs are essentially 3 different stone wall assemblies, and the bottom cluster of graphs are 3 different XPS wall assemblies. And so we're looking at the vertical axis of how much water was stored versus the horizontal axis of the amount of time that passed throughout the testing, so we can see the drying rate. And so what you'll see that is from an initial point of view, right after the spray rack water penetration ended, you see that large dip, which is that initial drainage that occurs directly after the spraying. And then at that point, we're left with approximately a 200-gram difference between the stone wall assemblies and the XPS wall assemblies. And so you've got about approximately 800 grams in the stone wall, 600 grams in the XPS assembly, right? So already off the bat, it's not like you're seeing a significant amount of storage within these assemblies. If we take a look at the drying rate and the drying capacity, you'll notice that after 5 hours of being in this laboratory environment where we're not getting any help from air cavity or wind to help dry out these wall assemblies, that after 5 hours, both of the wall assemblies essentially have the same amount of water that is remaining to be stored within that assembly. And so what this demonstrates is that whether we're using stone wool or XPS, that firstly, even if it's behind an open joint cladding, we're actually not seeing that much water being stored within the assemblies. Again, unless you've got a condition where it's improperly installed, where there's detailing that is essentially enabling water to be stored in the assembly. And then the difference between a stone wool insulation, which is vapor permeable, versus a foam plastic, which is vapor impermeable, you know, we can kind of disregard that misconception that the stone wool is going to absorb a high amount of moisture, because in reality, there's a very small difference after the 5 hours, so 28 grams per meter squared, which is essentially 0.1 ounce per square foot. So very little difference in that. Yes.
So I guess as an example of a misdetailed facade that would store more moisture, I guess, would you state that an example would be like a Z-girt that's running horizontally with maybe the up leg in the wrong location, something that would then trap water as opposed to let it continue to drain out, so to speak?
Exactly. That's probably one of the biggest, you know, poor detailing that we see, that we could potentially see where water is being stored. That negative slope in that horizontal Z-girt is essentially going to hold water in place, and you're not able to have that drainage. And essentially, if you have that case, if that's the case, if you have that scenario in terms of the detail itself, it wouldn't matter if you've got a stone wool, a foam plastic, or whatever type of insulation you're there. That negative slope in that Z-girt is going to be able to hold moisture no matter what insulation you have there. And it's not going to be able to drain out of the assembly.
Thank you, Alejandra. Just before moving on, I was reading the chat, lots of interesting comments. I want to go over them extremely quickly. So the first one was that in the CPhD exam, there was an emphasis on locating the air barrier on the interior. I cannot really comment on this, but what I will say is good practice is to put it on the exterior because it's easier to detail. However, the good thing with air barrier as opposed to vapor barrier is you cannot put too many air barriers. You don't want double vapor barriers, for instance. For air barrier, you can have a primary air barrier on your sheathing and a secondary air barrier on the interior side. Let's say you seal your gypsum finish and you seal maybe your vapor barrier. So there's no problem with having several air barriers. And also, ultimately, the location of the air barrier will be depending on the type of assembly, you know, and there might be some specific example where it makes more sense to put it here and some other example where it makes more sense to put it there. Another question was about in the wall one, which had the BAT class 2 vapor barrier, no exterior insulation, if there was not a risk for buildup, a moisture buildup problem in the gypsum board. So it depends on the climate zone. Obviously, the wall that was showing only a little bit of moisture getting inside the wall, yes, potentially could be a problem, but ultimately the idea is that diffusion will bring so little moisture that sure it might condense, but because it's so little, as long as it can dry quickly, really quickly, it's not necessarily a problem. But for sure, depending on the climate zone, it might be a problem. And finally, a last comment was about hot and humid climate. So, and asking if in hot and humid climate, it would be better to locate the bat on the other side. So basically, when I was talking about pushing away the bat against the sheathing or against the interior finish. So what I would say is the location of the bat, no, it should always be located against the sheathing just to avoid this risk of having air looping in a cavity between the sheathing and the bat. In a hot and humid climate, where the moisture drive goes from outside to inside, where it's hot and humid outside and drier and cooler inside, basically the idea of controlling vapor will be done differently. But you will use a water resistive barrier with the lower permeance. It will not be too low because you want the wall to be able to dry out, but it should be lower in order to limit the amount of moisture getting in the wall. So the location of the bat will remain the same, but you will basically deal with the control moisture a little differently in a different location. So getting back to the presentation. So basically now I would like to talk about hygrothermal modeling quickly. I think some of you might already be, aware of WUFI and knows what it is. At least the ones who don't know, maybe they have heard about dew point. So dew point calculation is basically when you try to assess the risk of condensation, but the dew point calculation is a very simplified method that will only consider relative humidities, temperatures on both sides of your assembly, the thermal resistance of your material and the permeance of the material. It's done in steady conditions. The benefit of hygrothermal modeling using WUFI, which is a German software, but which has been co-developed with Oak Ridge National Laboratory in Tennessee, is that it allows for dynamic analysis. And by dynamic, I mean that you can basically run the analysis using a hourly climate file for a period of several years, potentially using real climate data for outside, real indoor conditions for inside, and you can assess basically the performance of your assembly within this dynamic condition. It's not a software that is used for simulation. Always very important to have that in mind. Unlike energy modeling, which sometimes is used to do to predict energy consumption, you will not do hygrothermal modeling to predict real conditions, because first, you don't know what the future of the climate is going to be. But more important, when you design for moisture, you don't want to predict reality and make sure your wall is good most of the time. You want to design so your assembly, or whether it's your wall, your roof, can handle extreme conditions. Because if your wall is good 90% of the time, but every time there is a big storm or there is a big snowfall, then your wall gets wet and cannot dry enough, it will not be useful to you that it's good 90% of the time for, so it's done to predict extreme scenario and see how an assembly can react to extreme conditions. And the benefit of hygrothermal modeling is it can also look at solar radiation, actual rain, wind exposure, and it can look at water leakage, air leakage, and so on. So a lot more interesting than a simple dew point analysis. Now, if you, on the slide I wrote, it's easy to use, but very complex to use. I don't know, some of you may have tried or may be users of WUFI. And if you use WUFI, you will know what I mean by that. Basically, the user interface of that software is really easy to use, is really good. But the understanding what we do with the software, the results, and how to model things, this is what's really complex. And so this software is a good information, but it has its limitation. Number one limitation is it's limited to 1D calculation. So it wouldn't take into account thermal bridging or like connection from wall to slabs. There are other versions of WUFI called WUFI 2D or WUFI passive, which can do 2D or 3D, but they get very complex, so it's not used as much. It's difficult to determine initial conditions with WUFI because basically you can model your wall, but especially if you work on a retrofit, for instance, knowing the actual materials you have on site, their properties, their condition of moistures and so on can be quite tricky. And the choice of the material. Some materials, it doesn't matter if you use a generic material or a material from one brand versus another, because the difference is not that important in terms of moisture. But if you think about masonry, for instance, and retrofit of old masonry buildings, for instance, there's so much differences between bricks, even within the same building, or between bricks made in early 1900 versus 1930s and so on, that it's very important to choose the materials properly. So I just want to run you through a few things to illustrate. Earlier, I was talking about this idea of ratio of insulation, if you remember, in terms of vapor diffusion. So the risk is in a wall assembly, especially in a heating dominated climate, is that you have moisture going from the warmer and humid inside towards the cold and dry outside. And so the risk is to have this moisture going through your wall and potentially condensing on your cold sheathing. And in order to keep to make sure this doesn't happen, is to keep your sheathing warm enough by using exterior insulation. And the idea here is I want to illustrate this concept, this idea, and especially show how different ratios will do different things. And so here we're going to look at 4 different walls. One wall with a batt filling a 6-inch stud cavity. Then we're going to look at, so no vapor barriers in order for this illustration to be clear. We're only considering class 3 vapor retarders. So latex paint on the exterior side, pretty much what you would do in New York City, climate zone 4. You wouldn't really use necessarily a vapor barrier, so you would just rely on the paint on your gypsum sheathing. So we're comparing a wall with a batt insulation filling a 6-inch cavity. Then we are looking at the same wall, but we're adding a R4 CI on the exterior side of that wall. In this case, stone wall, which is important because it's vapor permeable. Then we're going to look at 2 inches, so R8 on the exterior, and then we're gonna, but with less bat, only 3.5-inch bat. So we increase the amount of exterior insulation, but reduce the amount of bat insulation. And then 6-inch bat plus 2 inches of exterior insulation for the R24, R8. If we look at the total water content in the wall, so this is what the graph is showing. On the x-axis, you have the time in days going from October 1st, 2020, all the way to October 1st, 2023. On the y-axis, we're looking at the water content pounds per square foot inside our wall as a whole. Like if we were taking our wall, trying to take all the moisture within this wall and measure how much we have per square foot. And so what you see is every winter, as you go winter, the amount of water in the wall increase. During the summer it dries. Next winter it increase again, following summer it dries. And the third winter it increase again, and following summer it dries again. And we see with all this wall, it's really repetitive. There is no continuous increase of moisture or anything. So it looks good. The thing we see though here is that in terms of total water content in the wall, it's pretty much all the same. There's no clear difference.
Antoine?
Yeah.
I just wanted to give you, we're about 5 minutes before we hit the hour. Just to,
I know it's, I see that it's terrible.
Yeah.
I will go much faster on this thing so Alejandra can cover part 2. So if we look now at the relative humidity on the interface of our gypsum sheathing. So we know as moisture is flowing from the inside to the exterior side, what can happen is condensation to occur on the interior side of our cold gypsum sheathing or colder gypsum sheathing. And so potentially what we want to do is to measure the relative humidity there to see if there is a risk to reach saturation and potentially having this vapor water to condense. And what we see is if we compare the same walls and we consider 80% as a threshold, I will come back to this in a minute, we see that now these different ratios give a different relative humidity on the interior sheathing. So basically in terms of ratio, the more interior insulation versus exterior insulation, the worse the relative humidity is on our sheathing. In order to avoid moisture issues, you can easily imagine that what you want is a lower relative humidity. So the higher the relative humidity, the worse it is. And we see in winter when we have only bat, definitely our relative humidity is really high. Now there is a standard that talks about how to do moisture analysis, and this is ASHRAE 160. In this case here, I'm showing the 2009, but there is a newer version from 2016, and there is actually an even newer version that will soon be available. And so basically what it says is when you do moisture modeling, you should account for 1% of rain leakage. As we said earlier, even if we built our building really well, there will be some leaks here and there. And therefore, this standard tells you that when you do a moisture modeling, you should account for 1% of the rain that actually reach the surface of your water resistive area. So that's what we've done in the following analysis. So now we've understood the ratio is important. Let's look at the impact of various materials on the insulation material on the exterior side of our assembly. So Alejandra was talking about, XPS that was vapor impermeable. I think at least she was talking about this if I recall in her part, but at least she was comparing stone wool and XPS in terms of drying. So now let's look at the same walls, same 6-inch bat in the cavity, but we have in the first gray wall R8, mineral wool on the exterior side of our sheathing. Then we have a new wool now, which is the same R value, but with XPS on the exterior side, which is vapor impermeable. And then ISO on the exterior side, which is also vapor impermeable. And what we see is, if we compare the relative humidity of our different, the sheathing with these different scenarios, we see that the stone wool, because it allows for drying, basically the sheathing ends up with a lower relative humidity. Here, we're not considering the water, which is recommended by ASHRAE 160. So basically what it says here is in perfect condition, sure, the relative humidity of the sheathing will be a little higher with XPS and ISO, but it's still okay. We're still quite good. If we consider 1% leakage now, because we have insulation which is vapor impermeable, basically we get in the scenario where we have water that penetrates behind the insulation, let's say around a fastener, around a window frame, maybe because the boards of the insulation are not perfectly tight and a little bit of rain penetrated there. Now what we see is because the exterior insulation is vapor impermeable, this moisture that penetrates and reaches the sheathing is unable to quickly dry. And we end up with relative humidity levels at the sheathing now that are much, much higher with the insulation that is impermeable. We see with the stone wool, even though we had this 1% of water leakage behind the insulation, because it's vapor permeable, it's still able to dry quickly enough that our relative humidity at the sheathing remain quite low at all. Now, and for sake of time, I won't go too much in depth, but basically this 80% relative humidity is basically explained. It's in ASHRAE 160 what it means, but there's basically a threshold that says that your sheathing or your sensitive layer should not have a relative humidity in average, which remain above 80% for a certain amount of time, like for 30 days, when the exterior temperature is, when the temperature of the layer, sorry, is between 41 degrees and 1 degrees. Basically, it's looking at, it's saying that the relative humidity should not be too high for a long period of time when the temperature range is basically favorable to mold growth. Because if you meet this condition, then you will have mold. If you don't meet this condition, meaning your relative humidity is higher than 80%, but for not too long, let's say 2 weeks instead of 1 month, well, then it might be okay. You may have a little bit of condensation here and there, but because it's able to dry quickly enough, it's not going to create moisture issues. I want to point out that there is a newer version of the standard, which has a bit of a different criteria, which is basically which introduced a mold index. For the purpose of this presentation, I didn't want to get into this here because it's a little more complex, but I definitely want to point out that there is a newer version of that standard with a updated criteria. And so now if we look at same walls, but with the actual criteria, what we see is that with the stone wool wall, again, because it's able to dry, because the exterior insulation is allowing for drying, the mold growth criteria is never met. As you can imagine, based on what I was explaining earlier, with the XPS wall, now we have this 1% leakage penetrating behind the insulation, reaching the water resistive barrier, because the impermeable insulation is not allowing for drying, and because there is not enough exterior insulation, the sheathing is at that temperature range where you could have mold growth. And you see this black line appearing, and this black line is showing every single day where this mold growth criteria is met, which Alejandra was pointing out with the mouse. And same with ISO. So the idea is not to say, obviously, that you cannot use XPS and ISO, but basically, when you use exterior insulation, which is vapor impermeable, the ratio of exterior insulation to total insulation is even more important, because now you have to account for the fact that if water penetrates behind the exterior insulation, because it will not be able to dry quickly, it might create problem. And this goes back to the balance, the moisture balance. It's okay to have wetting as long as you can have at least as much drying, and that this drying can occur quickly. And well, when you use exterior insulation products that are vapor impermeable, the drying is going to occur slowly, and therefore you need to make sure you don't have temperatures which are favorable for mold growth, or that you don't have much water penetrating and reaching your sensitive layers.
So I might interject. This is Todd. Obviously we're hitting the hour. I might suggest, Andreas, if you're okay with it and the audience is okay with it, that we continue to go forward. And if people need to chime off because they have other commitments, we will not be offended. But I think rather than have us rush through the balance, that we should go through it. And for those people that are willing to stay on, that's great.
Yeah, and we're gonna send a recording afterwards. So anyone who peels off earlier will have the recording later then. So it's no problem.
Great, thank you.
Great, thank you. So now that Antoine has kind of walked us through that theoretical performance analysis using WFB, which, as he mentioned, is not necessarily a tool to predict performance, but rather to, assess relative risks and compare different types of wall assemblies, to further validate the performance of stone wool insulation in exterior application. What I'm going to be doing is I'm going to be showcasing some in-situ case studies to evaluate this performance. And so I'm going to showcase 2 different research projects in this presentation, considering different types of wall assemblies and different climates. And so the one thing that I want you guys all to keep in mind when we're going through these in-situ case studies and then when we're evaluating the performance of an assembly, what we're really wanting to look at is that long-term durability and that making sure that it's assessed with respect to relative risk as opposed to being judged solely on a pass-fail basis. So what this means is making sure that we're taking into account all the critical layers within the assembly, which would be the most susceptible to moisture and with the highest likelihood of seeing condensation or moisture accumulation. That we're considering the exterior temperatures or the temperatures of the layers if and when a wall is experiencing high levels of moisture and how that relates to potential failure and potential damage or mold growth. And then also accounting for how long a wall is experiencing high moisture levels. And then specifically when we're thinking about the type of exterior insulation, you know, how long is the exterior side of the assembly holding on to this moisture, and how long or how quickly rather it takes for that moisture to dry out. So the first study that I'm gonna be showcasing here was located in the Pacific Northwest. And so when I'm speaking to the Pacific Northwest, I'm talking both US side and the Canadian side, but essentially marine climates that are climate zones 4, 5, and 6. And so one of the most important climatic characteristics of this climate is that these climate zones experience consistent rainfall events with limited time in between them to allow for drying, which means that there is a higher likelihood of a wall assembly in these climate zones to potentially hold on to more moisture because the climate doesn't allow for that much time in between to allow for drainage and drying. And so when we talk about the performance of stone wool, given some of the misconceptions around its performance and durability when it comes to moisture, you know, validating the performance in a heavy rainfall climate would definitely serve as one spectrum of a worst case scenario. Okay, so the study that I'm going to showcase here is essentially a test hut study that was conducted in Vancouver, Coquitlam, which is just outside of Vancouver, and it's the Vancouver Field Exposure Test Hut Facility. And so we conducted this research again with Building Science Laboratories, now RDH Building Science, and essentially the purpose of this study was to evaluate the performance of the stone wool insulation used as an exterior insulation and compare its in-situ performance with different insulation types, and as well as also assessing the potential for moisture-related risks. So this was a 2-year study. And so if we're looking at the image here, I'm referring to these 3 wall assemblies here. So we've got the stone wool wall, we've got the two wall assemblies that are next to them, and so we've got an XPS assembly and a polyiso assembly. And so based on these ones have this black facing on top of it, which is a vapor permeable facing over it, just because in terms of we installed an open drain cladding on top of these assemblies, and so that was just for a UV protection membrane, which the stone wool insulation did not need in this case. And so what I'm also showcasing here, as I mentioned, is that, you know, we also wanted to assess the potential for moisture-related risks. And so to do so, what we did was we included intentional wetting, and this is the intentional wetting mechanism that was in all 3 of the assemblies. To compare, I guess, the in-situ versus the theoretical, these are 3 different wall assemblies that have similar layers than what Antoine showcased in his WIFI analysis. And so in this case, all of the assemblies included batt insulation between the steel studs. They used a 1/2-inch gypsum board as the exterior sheathing. The fluid applied membrane on the exterior side, so the air and water resistive barrier was fluid applied and vapor permeable. So we're looking at approximately 12 US perms. And so really what was different about these assemblies was only the type and thickness of the exterior insulation. And so for the stone wool wall, we used 2 inches of rigid stone wool insulation, which is vapor permeable, that had an R8. The XPS wall, we used 1.5 inches, which had an R7.5, and XPS is more of an impermeable insulation. And then the last wall, which was a foil-faced polyiso, definitely an impermeable insulation, which was an R9. And so essentially, we tried to get, first of all, common thicknesses available in the market to be somewhat similar in terms of overall thermal performance for these layers. And then again, just to point out, we don't have a dedicated vapor barrier in these assemblies. We've got latex paint on the interior side of that drywall, which is acting as the class 3 vapor control layer within these assemblies. And then we selected to use that vapor permeable water resistive membrane so that essentially we could actually assess and see the performance of how the different insulations impact the performance of the assemblies versus if we had put something that was low perm for that membrane, then really that membrane would be the driving performance indicator as opposed to the type of insulation that we're using. And so what we did was, because it was in-situ, we had a series of sensors put into these wall assemblies, basically to look at the most critical parts of the assembly. And so this is what's showcased here on the schematic that we see here. All of the assemblies had the same sensors in the same locations. And so it was a combination of relative humidity and temperature packagers, also moisture content and temperature packages, some temperature sensors, and moisture content pins. And so one thing that I want to just highlight, which is common practice when it comes to in-situ sensors and monitoring, because we use the gypsum sheathing, it's actually really difficult to measure moisture content or relative humidity of a gypsum sheathing. And so what's commonly practiced is that they used wood wafer pins. And so that's what we used to measure in lieu of actually measuring the gypsum sheathing. And again, this is very common practice when it comes to in-situ monitoring programs. And then that wetting mechanism that I demonstrated on the slide before is what we see here in this blue line. So essentially we've included it to the bottom of the wall. And so the reason why we have it on the bottom of the wall as opposed to the top of the wall is because we wanted to be able to assess the wall assembly in two different ways. Basically, in normal conditions with no intentional wetting, we'd be looking at the top portion of the wall. And then when we want to assess relative risks with the intentional wetting, that's when we're looking at the bottom of the wall, and so that this intentional wetting wouldn't affect the normal operating condition setting. So the graphs here is showcasing the performance under normal operating conditions. And so the first graph here, both of them are looking at the moisture content, basically on the exterior side of that sheathing and the interior side of that sheathing. And so the first graph here, we're looking at the exterior side of the sheathing. So essentially between the membrane and the insulation. And then on the next figure, we're looking at the interior side of the sheathing. So essentially the interior side of the gypsum sheathing in between the sheathing and the batt insulation. And so what we've seen here is that when it comes to portions of the year where we're experiencing outward vapor drive, all of the assemblies on the exterior side of on that interior side of the assembly are experiencing similar performance in that case, where we're definitely seeing an increase in the colder months. And so we're looking at here December, January. This is similar here in year 2, although not as high. This is the difference in the high peaks can be associated to the difference in temperatures perhaps within the 2 years, but also just within the drying of that built-in moisture of these assemblies could also have an effect that by year 2, a lot of that initial moisture could have been dried out already, right? And so what I definitely want to showcase here though is the moisture content on the exterior side of that sheathing. So again, this is under normal operating conditions. We don't have any kind of additional intentional wetting. This is just seeing how the wall is performing, how is vapor diffusion able to assist in the drying out of these assemblies, knowing that we're experiencing outward vapor drive. And so what we're seeing here is that the stone wool assembly, which is the green line, it's pretty steady throughout the year, versus the XBS and the polyiso assemblies. When it comes to these winter conditions where we're experiencing the high outward vapor drive, they're actually seeing high spikes in terms of that moisture content. And essentially what's happening is that because we're using, in this case, the water resistant barrier was vapor permeable, the insulation layer itself is acting as that vapor control layer. And so as vapor is diffusing outwards, once it passes the sheathing and that membrane, it essentially has nowhere to go once it reaches that impermeable insulation, versus the stone wool insulation, because it's permeable, the assembly can continue diffusing out, drying outwards, and also kind of as well as promoting drainage. The graphs on this slide here are now looking at when we added the intentional wetting scenarios. And so we looked at multiple different wetting scenarios throughout the 2-year study. Some of them happened in the summertime and some of them happened in the wintertime. And so the first graph here is for a summer wetting event, and the second graph here is for a winter wetting event. And so essentially what we see in the summertime is that this red line here represents when the intentional wetting event happened. And then the next couple months, probably about a month and a half or so, just to demonstrate, to assess the drying capacity of the assemblies. And so what we're seeing is that in the summer months, for the most part, yes, because of that initial wetting event, you are seeing that increase in moisture, obviously, because you're adding that liquid water to the assembly. But for the most part, you're seeing more or less consistent drying trends, specifically between the stone wool and the XPS. The polyiso, because it's an even lower vapor permeable insulation, takes a little bit longer to drain and dry out. But this is in the summer conditions. However, when we look at the winter conditions, where, as we know from normal operating conditions, is when this assemblies were most susceptible to potential risks, you'll see that there is more of a significant difference in terms of performance. Again, this vertical red dotted line is showcasing that exterior wetting event. And what we're seeing here is that the stone wool assembly definitely dries out much quicker. That initial drying happens much quicker. And then throughout the rest of the winter, the relative humidity at this interface is definitely more consistent, versus the polyiso and the XPS assemblies essentially taking much longer to reach that more equilibrium, whereas in comparison to the stone wool. Again, this is going back to the concept that because they're vapor impermeable and we're experiencing, not only the intentional wetting, but the outward vapor drive, the assembly is not able to dry out to the exterior as much as the stone wool insulation assembly can, because it's vapor permeable. So the next study that I wanted to highlight, changing climates a little bit here, we wanted to look at what happens in a hot and humid climate. So we know that these climates are definitely more susceptible to damage. Typically, their biggest challenges that, for the most part, most of the failures, most of the decays are always basically associated with water. They also have high solar radiations and inward vapor drives into the assembly that can definitely add that extra moisture to the assembly and potential damages here. And so when I'm talking about hot and humid climates, I'm basically referring to the most moist climate zones 1, 2, and 3, basically below that hot and humid threshold that you would normally see in the ASHRAE climate zone graphs. And so these are just here some examples of typical failures that you would see in buildings that were built in these hot and humid climates. And so you can see, definitely corrosion at the steels and the fasteners. Image 2, I think, is one of those common images that we've seen from buildings in the past that have used vinyl wall coverings on the interior side of the assembly. We know that in hot and humid climates, you definitely don't want to have the vapor control layer, the vapor barrier on the interior side of the assembly, because this is what happens when you do have it there. And then this last image here is just demonstrating, how susceptible building materials, if the assemblies aren't designed or detailed properly, you can definitely have damage when it comes to water. And so in this case here, this was, a stucco assembly that had just a loose laid water resistant barrier behind it, improperly detailed. And what we're seeing is that OSB sheathing definitely was completely saturated. And this was something that happened, you know, just within a short amount of years after the building was set. So just basically highlighting that hot and humid climates definitely are susceptible to moisture problems. And so, you know, the use of stone wool insulation, again, because it's vapor permeable, there's obviously concerns in the industry of whether or not it's going to be adequate there. And so what we did was we conducted another field study. This time here, we're looking at a test facility in Charleston, and this study was conducted with Oak Ridge National Labs at their NET facility. And so basically this is in climate zone 3, just below that hot and humid threshold according to the ASHRAE graphs. And so we looked at 3 different wall assemblies. The first one was a CMU wall with interior insulation. The second wall was a steel stud assembly with exterior stone wool insulation and that brick veneer. And then the last one was a wood stud assembly, again with exterior stone wool insulation and vinyl siding. Both the brick veneer and the vinyl siding insulation assemblies did have an air cavity behind the cladding to promote that venting and that ventilation behind the cladding. And then just for the sake of focusing on rain screens and what we talked about during this presentation, I won't be covering the results of the CMU wall assembly, but that information is available if you are interested. So similar to the previous assembly, these walls were also had a series of different sensors and monitoring locations within the critical parts of the assembly. So again, including, you know, the back side of the cladding, the exterior side of the insulation, the interior side of the exterior insulation in between the membranes and the insulation, and then looking at the interior conditions on that exterior side of that interior drywall. Obviously, because in hot and humid climates, there is a greater concern for inward vapor drive. We wanted to see, is the interior getting high amounts of moisture? And if so, how is that affecting the performance? And again, basically to not have, I think Antoine mentioned it about selecting the right water resistant barrier for hot and humid climates. Typically you'd want something that is low enough to kind of limit the amount of inward drive, inward moisture, but also high enough to allow for some exterior drying. And so typically we're looking at a perm rating that would best fit somewhere between maybe, you know, 5 US perms up to probably 10 US perms. In this case here, I'm going to showcase the results of what happens when we use a WRB that has a perm rating of approximately 10 perms. I think that was actually slightly higher, maybe about 11 or so. So just to, again, basically see how does the stone wool impact the performance, knowing that you would likely have perhaps a slightly lower perm rating for the WRB. And so here we're looking at 2 graphs. So the first graph here is what we're calling wall 2, which is the brick veneer wall. And the second graph here, which is wall 3, which is the wood stud wall. And so definitely what I wanted to highlight by showing these graphs is that when we're looking at the relative humidity, which is here on the vertical axis, and the time, the days on the horizontal axis, these different lines are representing the different critical layers where we were monitoring the assembly. And so for the brick assembly, we know that brick is a highly absorptive cladding. And so definitely when we think about inward solar-driven moisture, inward solar-driven moisture, there's definitely a higher capacity in these types of assemblies because the brick can actually hold a lot of moisture, right? And so what we wanted to make sure is to see, well, how much moisture that is being absorbed by the brick is actually being driven into the assembly, and whether or not that's impacting the performance. And so the first thing to point out is that when we look at the results of the amount of moisture in the actual exterior insulation, which is the red line here, which is that exterior side of the insulation, and then that gray line there, which is the interior side, so essentially the back side that's towards the actual sheathing. What we notice here is that there is obviously experiencing some highs and lows in terms of moisture, but overall, these levels are within acceptable conditions. We talked about, 80% kind of being that threshold of where we don't want the materials to surpass in terms of relative humidity. And so these are definitely well within that threshold. And I think that's definitely showcasing the stone wall's ability to actually drain out any kind of moisture. And it also showcases the fact that the stone wall is designed to be not non-hygroscopic, which means that it's not actually holding on or absorbing moisture that can be found within that air cavity, which in this case here was going to be slightly higher because, again, you've got that highly absorptive moisture, hot and humid climate. So we know that that air behind the brick veneer was actually had a high moisture content, but we're seeing that the insulation itself is not absorbing that moisture content from the air. We do see this purple line here. Again, we're seeing that interior drywall, so that exterior surface, just to see if there is a lot of moisture being driven inwards. Is it reaching that gypsum, that interior drywall? Is it seeing very high levels? Again, we're seeing ranges in and around the 80% as the high part, which is indicative that we're not seeing that much inward drive, basically because the insulation is not holding on to that moisture and it's able to drain and dry. And so what that means is that there's less potential for mold growth or any kind of moisture-related failure on that interface. Similarly, here we're looking at that wood stud assembly with the vinyl cladding, with the vinyl siding. Again, just for, to speed up the time a little bit here, essentially what we're seeing is that, there's definitely some diurnal effects in terms of, you see the red and the blue lines, which is the relative humidity in that exterior insulation. You see the diurnal effects of, relative humidity kind of spiking during times of the day and then drying out. But because these durations of high moisture are not long at all, they actually quickly dry out. Basically, this is showing a 24-hour running average. If we were to actually just have every single hour plotted here, these diurnal effects, you would see much more spiking, which essentially means that yes, the assembly is kind of getting those higher peaks because of the solar drive, but quickly draining and drying out. So we're not seeing those effects. And then again, this gray line here is actually showcasing that interior drywall and well within the ranges of 80%, indicating that there's not a concern for that inward drive for potential damage and mold growth on the interior side of the assembly. And so I think this is important information to consider, because when we think about how assemblies are typically designed for hot and humid climates, for the most part, you definitely want to have that vapor control layer towards the exterior side of the assembly, so essentially on the warm side of the assembly, in contrast to colder environments where that vapor control layer should be on the interior side. And so typically what we see in these climates that use exterior insulation, they'll definitely rely on using a foam plastic, just because you get that quote unquote all-in-one material in that case there. But for those that want to use stone wool, this is essentially validating that you can use stone wool, and the vapor permeability of the stone wool is not gonna cause potential failures to these assemblies, as long as you're pairing it to with an appropriate WRB. So this takes us finally to the end of the presentation. I just wanted to leave you guys all with some final takeaways. So the first and foremost is the balance of moisture is critical when it comes to enclosure design. You definitely want to ensure drying is higher than the wetting. That vapor permeable stone wool exterior insulation enables drying, and it actually does not trap moisture, unlike what is commonly misinterpreted in the industry, for some in the industry, I should say. We can definitely use advanced moisture modeling as a good tool to adequately assess performance of wall assemblies and make basically informed choices when we're selecting our materials and which materials to use within our assemblies. And finally, the misconceptions against the use of stone wool insulation are just that. They're only misconceptions. We've got, there is in-situ monitoring that is validating the performance, specifically in rain screen applications where the perception is that it's going to experience a lot of a lot of rainwater onto them. And so even with high moisture loading on exterior walls, it is an acceptable solution to use in all types of climate zones.
Well, first, I want to thank both Antoine and Alejandra for presenting this today, and I want to thank the audience for sticking through it. I know I'm going to use a pun now. I know it was a lot to absorb, but I think it was all really good information. And so we will open it up to questions. I think Andreas, if you want to take folks off mute and keep people the opportunity to chime in, we're totally fine with that. If people need to jump off, that's fine too. I mean, I just want to make sure everyone knows that we're really appreciative that you guys sat through today, and hopefully you got a lot out of it.
Yeah, so I would like to thank you guys. So I unmuted, so everyone can unmute themselves if you have another pressing question. We'll keep it open for a little while. And
I have a quick question.
Mm-hmm.
It's not really applicable to the topics you guys were covering here, but with rock wool in general, I know when in the Passive House Accelerator happy hours, the conversation a lot of times turns to embodied carbon in materials. And I know that rock wool, I guess with the manufacturing of the material itself, not with the ingredients, but with the manufacturing, it can be considered a very high embodied carbon material. And I'm wondering if there are methods to the manufacturing that you guys have looked at and have addressed this and can reduce that embodied carbon, or if that's an issue at all for you guys.
Alejandra, I'll let you.
I'll take this question. Yes, I mean, obviously in the industry, embodied carbon is definitely where the industry is kind of, when we think about high performance, when we think about sustainability, that's kind of the topic of conversation right now. And yes, we do definitely, it's important to evaluate the different embodied carbon of different insulation materials. I would say that mineral in general, or at least rock wool products, stone wool specifically, they will have a higher embodied carbon than some other because of the manufacturing process. As you just mentioned, the reality is, you know, to manufacture stone wool or mineral wool, you essentially have to melt stone to be able to, you know, get all these additional benefits like fire, acoustics, durability, and all that stuff, right? So definitely it can be higher than some of the than some other insulation types, but I would say it kind of falls in the middle range because it's definitely also lower than some other ones. When we think about perhaps some of the foam plastics, perhaps not all of them, but some of them can have very high embodied carbon, perhaps not associated to their manufacturing process, but associated to potential off-gassing from these insulations, both during the manufacturing process, but also during, you know, the in-use time of these buildings, of these assemblies. And so I guess to answer your question specifically, I think rock wool as a group is constantly investing in research and innovations to improve our manufacturing process to be less carbon intensive. We've got some examples that we've showcased in our sustainability report. I don't know if you've had a chance to read that yet. That was launched earlier this year, but you know, we're definitely investing in different technologies as a group, different innovations to be able to lower that embodied carbon. So I guess to directly answer your question, yes, it's something that we're actively looking at, something that is definitely top of mind for us. But overall, I think the key is when we're assessing the embodied carbon of different materials is really to just also look at the big picture, make sure that we're comparing products that in the end of the day are also going to perform as you need them to perform as well.
Yeah, I think that's a really good point. And just to kind of chime on to that is that, you know, when you look at the thermal stability capacity of stone wool and the fact that it can perform for, let's say, a century, there's a tremendous amount of carbon savings through its lifespan. So, you know, there is more to just looking at embodied carbon to embodied carbon. And I think Alejandra makes a good point because there also needs to be considerations on fire safety for occupants, acoustic capacity for occupants, building durability and resiliency through weather events, through wetting, what we just talked about here today. So it's not you don't want to be siloed in that discussion. But I think also to Alejandra's point, we continuously look at opportunities and ways that we can reduce the carbon within the production process of stone wool.
My question has to do with below grade assemblies, and I did a retrofit for a crawl space, and in my research I was just about to use mineral wool up against stego wrap, crawl space wrap, when I found an article, I think it was Green Building Advisor or something, that just said, no, you can't do that because you'll get condensation, and so possibly behind that. And so they suggested first use spray foam, and then, to get the dew point away from the mineral wool. Do you have any thoughts about that you want to share?
Personally, fully understand the conditions, so I don't know if Alejandro told you better, you understood better than me. It's a below grade interior installation, or is it exterior to the concrete?
It's interior, so it's an existing building retrofit. So it's a CMU wall,
Yeah.
Below grade, and two flanking crawl spaces to a basement, a full basement area. And we were moisture sealing, air sealing, and insulating those crawl spaces.
Okay, so the crawl space is conditioned. It's a basement, basically.
It's basically connected to the house, yes.
Yeah, okay. And so can you repeat, I'm so sorry, but I'm getting pieces one after the other. Can you repeat what the issue was you read about?
So the issue, I was going to do the stego wrap, poly wrap for the moisture barrier and air barrier. And then I was going to put the insulation using mineral wool. In my reading, it said, don't do that because you'll get condensation behind that mineral wool. And so first, even though I don't like using spray foam, I finally I said, in this condition, I need to use a couple of inches of spray foam before I get that mineral wool.
Yes, okay, I understood now. So yes, for sure, like a flash and bath type solution where you will have the spray foam against the CMU, and then the rock wool insulation is good. Basically, the issue here is that you have inward moisture drive. So the moisture is coming from the ground through your foundation, through your insulation. So if you put a 6 mil poly, the risk is to eventually have condensation there and trapping moisture, basically. So one way of dealing with this will be to use a smart membrane. So a membrane which basically could be used as, will allow the moisture to flow through and dry toward the inside. So then it's removed using ventilation. An example of a product like this will be CertainTeed membrane, for instance, or a product called In-situ. I see there are questions in the chat. So Ben was asking about the trend of basically higher air exchange. I guess this is because of it, or opening windows. I think it's moisture issue. Well, hopefully we're opening the window and so on, but hopefully we're still somewhat controlling relative humidity on the inside. So I think it could become a moisture issue for sure if we're looking at a very hot and humid climate, for instance, where we actually bring a lot of moisture inside the building. But I think we still some air conditioning to condition the air and hopefully control the relative humidity. In cold climate, like or like colder climate like New York, or even where I'm at in Toronto, I guess that's potentially a problem we could see in the summer, in the winter, sorry. But I think the amount of moisture that we bring inside a building like this, in the big volume of the interior of the building and the mechanical system, I don't expect it to be an issue in most cases, but it's definitely an interesting point. I think it really depends how much air we are bringing inside the building by ventilating it more or by opening windows. But I think we should be able to control it. But definitely a good point. And then the last question was about our values. Comfort board 3 inches installed inside the cinder block, I guess against the cinder block walls, and then 2x4 framing holding R15. And I guess the question is about if it provides an R27. so the answer to that question is no, because the comfort bat installed between wood frame with some sort of thermal bridging. So the effective thermal resistance of the bat will be downgraded by the wood framing. And therefore the nominal insulation value for sure will be R27, but the actual effectiveness of the insulation will be a little lower in this case. It will have to be calculated.
So I think the second part of that question was also, would that assembly need an interior vapor retarder?
So if it's a basement wall, like I understand, I think it would be the same comment as the discussion we had with Laura. If you're using only vapor permeable insulation, we will recommend a smart membrane on the inside to allow the wall to dry inward, but make sure there's no moisture getting inside the wall. Otherwise, what actually Laura described, like a layer of spray foam or foam boards against the cinder block, and then mineral wool insulation over it, to ensure that basically which then means you will not need any other vapor control on the inside, because the vapor control will be done by the foam itself. So either a mix, an hybrid solution with foam and vapor permeable insulation, or a smart membrane on the inside of the vapor permeable insulation.
I might I have got a couple things to close if people want to stick on. I want to highlight a couple things. I won't go through everything, but Alejandro, I want to highlight, if you have got control of the slides, just a couple last words from Rockwool. So just quickly, so I think many of you are familiar with our products. Cavity Rock is our semi-rigid product that's commonly used for exterior rain screens. I think it was used as the basis of some of the studies that Alejandro worked on. This has been used on a tremendous amount of passive house projects here in New York City, as well as standard projects if you want to advance. And we now offer a black-faced Cavity Rock product for open joint cladding. So as opposed to having to incorporate a separate membrane, this is not serving as a WRB, but really as an aesthetic for those open joint or perforated cavities. So just bear in mind that that is now available if you guys are working with those types of assemblies. All right. And then just you can click through these. These are just some highlights of projects that we've done here in New York with these products in mind. Some certainly being passive house buildings like this one here at East 86th Street, another passive house in Hoboken. And then we also have a rigid board product, whereas Cavity Rock was a semi-rigid product. This is a rigid board at 11 pounds per cubic foot. This would be used below grade, but it can also be used above grade for screw-through insulation systems. So to help maximize thermal efficiency, as opposed to using clips and rails and Z-girts in your facades, all you need to do is fasten your facade systems through the rigid board product back to the structure. And this is really adequate for light and medium weight claddings like ACM, porcelains, HPLs, things of that nature. And we're seeing traction here in the passive house community to help maximize their thermal performance. There's a couple of projects here to highlight. This is the Corona Queens Senior Housing Facility that used 4 inches of the Comfort Board 110 product. And there's a project coming up, hopefully with Magnuson Architects. I know Sarah was on the line earlier, where they're considering the use of Comfort Board 110 here as well. Just quickly on a support level, many of you might already be aware of this already. So we do have passive house details available, certified passive house details. But more importantly, you can reach out to us and have Antoine support you on future projects. So we offer complimentary building science services. So if you guys are running into challenges where you're concerned about dew point, moisture, condensation occurring in the wrong spot in your enclosures, we can run that analysis through WFI to get a sense of what and if there is an issue. We can run thermal bridge analysis of specific conditions using 2D and 3D therm and heat 3. We can also calculate effective R values for your systems based on the assemblies that you've got to incorporate the metal stud framing, thermal bridging, as well as the clips and rails that are in your exterior, and see what that degradation might be. So just feel free to reach out to me if you want to click to the next slide. I think that's got my contact information. We got some guides, but you can click to the end here. That's going to sum it up for me, and thank you again for everybody attending today and being patient as we went over the hour by a little bit for sure. Thank you, Andreas, for having us, and I'm sure we'll chat again soon.
Definitely. Thanks everyone for joining, and thanks to you guys for presenting. It was very good, I think.